Hello community, so great that you are back. We have a brand new AI research paper and we talk about the illusion of AI thinking, and it is from Apple. Yes, in some days we have the big Apple event, so I thought, hey, why not show you the latest research from Apple? So just to make sure, where are we? You remember we have here ARC AGI leaderboard and we have our LLMs, no? Our Claude Sonnet 4, our Claude Opus 4, and then we have our large reasoning models, with the thinking. And we have here Claude Opus 4 thinking with 8K and Opus thinking with 16K. And you see here on this benchmark, oh yeah, there are really jumps here in the performance, in the score. We go here from less than 2% with the max thinking of Opus 4 to almost 9% performance. So we are now examining, hey, are those large reasoning models are really worth the money? And I did my own test, and I have here Claude Sonnet 4 in the non-thinking mode, and I did here a test from my last video. And for example, here the answer was a 12-button press here for my elevator test. And then I did the same test here with the Claude Sonnet 4, but thinking with 32K, so here really for the Sonnet a maximum thinking amount. And then we came down to 6-button presses. So this is here the correct solution. 12-button presses is the incorrect solution. So you see, there is a significant difference if to activate the thinking process if you go with the reasoning models. Now, Apple calls it here the illusion of thinking. And they said, yeah, we know we have LLMs, but we never knew how they would go and find here the results. And everything changed here some years ago, when we had the first O1 by OpenAI, and then we had the R1, the reasoning models, and they had a thinking process, and we saw the thinking tags and end of think tags, and we could really see here the reasoning process, and some of those models had a self-reflection, and it was great. It was a monumental leap because we thought, hey, there's a true artificial reasoning happening, or it's just around the corner, But then here at the beginning of June 2025, yes, the research of Apple decided to ask a simple question. Is it really thinking, or is it just a very good illusion? Is it just a simulation of a pattern machine? And I said, is it possible? Is it possible? So let's have a look at the standard test that we run. The good old 100 years old MAT 500, AIM 24, AIM 25, AIM 26. And you always see if here, for example, in blue, the thinking is better here if you give it a little bit of time than the non-thinking model. AIM 24, and here we go with DeepSeek, the old R1. This is new, not the new R1 0528. This is the old R1. You see, the thinking were always better, and the more complex it got, that the thinking really improved here. And everybody, including me, I thought, hey, yeah, I go with the thinking models. Now, they ran here their own test, and they found here there's something strange because their results were inconsistent and confusing. So, what they found, there are 3 areas, more or less. An area of a low complexity of the task, of a medium complexity, and of a real high complexity where all the AI models, more or less, they just stop reasoning, they just give up. And they decided, here, we design a test, a very simple test, We just have here 1, 2, 3 packs, and we just want to move here 1 object, 2 objects, 3 objects here from one pack to the other pack. That's all. And we have now defined here a very clear test environment, and we just look here at the thinking that is happening here in our start thinking and end thinking token of the models. And if they looked at this, and they looked at Claude 3.7, not at 4, but okay, we have Claude 3.7. This here in dark orange is here the non-thinking, and here in blue you see thinking. So you see there's an error here. The first where we call it an very easy complexity. On the x-axis we have the complexity, so the number of the disks, so 1, 2, 3 disks that we have to move over. And if we have 1 or 2, both models are performing equally. Maybe even the non-thinking is a touch better, but both the same level. Then we enter a region here in blue, what I call here, or they call here, a medium complexity level. Now we have to move 4, 5, 8, up to 10 different disks here. So how we do this, that everything is in order, beautiful. So you see, there is now a difference in the performance if you have a look at accuracy at a given level. Okay, so great. Thinking has a better performance with higher complexity numbers within this medium complexity interval. And then we have a region where both models crash. Nothing goes anymore. The complexity crashes the model. You see the performance is of both models close to zero. And Apple said, that's interesting. Let's have a closer look. And they said, hey, what about here the length of the token? Huh? And on the y-axis, they give us here 5,000 token length, 10, 20K token length, because the assumption was the higher the complexity of the task, I mean, very simple, basic task, no? The more reasoning token or thinking token, whatever you prefer, the system will use. No, it will think through all possible permutation. And if you've seen one of my evaluation videos, you see, yeah, the reasoning process takes up to 8 minutes, for example. No? So we produce more and more tokens. The higher the complexity goes, yes, beautiful. But then, you know what's happening? There's a threshold. And exactly the threshold between the medium complexity and the start of the strong complexity, we see that the token that the system uses internally, the thinking, is reduced. And you say, why? If I further increase the complexity of the task, no, the token should go up. Why suddenly the model says, okay, this is it for me. That's it. This was my peak performance. I give up. So we have a decreasing amount of thinking token. And the same, if you want, happens here with Claude 3.7. We don't have the thinking process. Just the response length, it's also decreasing. This was interesting, no? And Apple said, okay, maybe this was just this particular benchmark test. No? So we do have to define a controlled test environment with multiple of those tests. And they said, okay, simple as this 4 puzzles. So we have this, yeah, this is called the Tower of Hanoi. Then checkers jumping or river crossing or block world. So you see 4 very familiar, simple puzzle environments. And this gave them a test environment. And they asked, first question is, hey, does this happen in all 4 different puzzle environments? And I think it was a brilliant move because those puzzles are absolutely controllable. No? Precisely dial up the difficulty, no? Because we just have disk. If you look here at the Tower of Hanoi, we are verifiable, absolutely here. We can check here the thinking step by step because some of those models really give us here still the thinking process. And you see the proprietary models, they are hiding their thinking procedure from us. Last time, O4 Mini was not showing me anything of their thinking. They were afraid to be transparent in their thinking mode, which I do not appreciate. And then, yeah, specific puzzle configurations are unlikely to be all over the internet, so we have no data contamination for very specific configurations. And now have a look at this. And now they separated this, no? The low complexity here in yellow, the medium complexity in blue, and the high complexity here in kind of orange. And so on top you see Sonnet, and here you see DeepSeek. So let's have a look. And yeah, I know Parset K is not the best perfect benchmark parameter, but this is published, so we have to go with this. And I said, yeah, okay, so we really see Claude 3.7 non-thinking. If we start now, hey, look, the performance goes up much faster than the thinking. So you could say if you have a low complexity task, go with the non-thinking model, it is faster and better. If you have a medium complexity, and this of course depends here on the definition of complexity, but for this 4 tests, it was defined. You see here, now really the thinking model is the power player. Now it says, yes, I'm so much better than the non-thinking. But if you enter here, what they call a high complexity, and this is just 10 disks, yeah? You have to move 10 different disks. Both model collapse to 0. It says, okay, this is it, I give up. And this is amazing if you think about it. And the same here for the open source model. So the result by Apple is now, published today, non-thinking models excel in simple problems, simple complexities. The thinking models here, the large reasoning models here, like the O3 or the O4, show advantages at medium complexity, while both models fail at a higher complexity, regardless of the compute allocation. You can give it 8K, 16K, 32K, whatever. It's not able to solve the task. So they say, hey, this is not interesting. So this thinking now seemed to be helpful, but we find it's extremely fragile. It could delay failure. It could move it a little bit here in this very narrow area of the medium complexity, but it could not prevent it. So therefore, Apple said, hey, those LRM, those large reasoning models, are not becoming general purpose reasoner, only within a very close window. And here you have again, because this was just the sum, here you have it now for each and every of those 4 benchmarks. And you see it's almost the same behavior. It starts at a different complexity for the different environments, but you have here, if you want, a yellow environment, real simple, then the blue, the medium, and then both model crash here in the hard complexity area. It's always the same behavior. So Apple said, this is interesting. So what does it mean now? If we have a collapse of reasoning model, if we just have to mount 10 disk, how is this possible? Well, they said, yeah, if they look closer at this critical point, and I showed you here the threshold already here in their visualization, they say, just as the problems become truly complex, if we increase the complexity, the model started to sink less. Remember we went downhill in the number of tokens for the syncing process. So this is now interesting. Somehow the model was aware it's not able to solve it, it's too complex, and just started to give up and use less reasoning tokens. And this is what Apple calls here the illusion of thinking. When faced with a problem beyond its reasoning capabilities, the large reasoning model doesn't even try harder to fail, it just gives up. And you see this behavior. And this is absolutely fascinating. And of course, the deeper reason it goes back here to the quality and the complexity of the pre-training data set of the model, but more about this later. And they said, hey, the sophisticated facade here of this reasoning, it totally crumbles and it defaults now to a shorter token saving output that could theoretically, and they show it, also be wrong. And I mean, really completely wrong. And this is not a solution. This is just that the LLM gives up. It is a very strange behavior that we see in this particular test. But Apple said, you know what? There's still something left. There's still something like we call a final twist. Because they had the last question. We have training methodologies. And I'm not talking here about a simple SFT supervised fine-tuning. We have this powerful reinforcement learning. This is our most powerful learning, our engine for learning. And now we tell the model the solution. I go there and I say, hey, look, this is the solution. So I give them as a human here, if you want, the recipe to solve it in context learning, few short learning. Can they now implement it? Can they now follow the given template in this high complexity regime? And what do you think? The result was it didn't help at all. The large reasoning model still failed. And you know what's absolute amazing in the negative sense of the word? At the same complexity level. So this was something where I thought, hey, this is now something new. This is something strange. No? I thought reinforcement learning pushes the boundary further, increases here the capacity to go to higher reasoning level, to higher complexities. And now Apple tells me, no, the reasoning model still failed, even with the reasoning templates, the solver, at the same complexity level. So this means, what do you think this means, by the way? I think it's a stunning insight, yeah? It is not just in a high-level problem solving, it's something much deeper, something much more fundamental. At a certain threshold, it's an inability to reliably follow here a logical sequence of steps. This is really something new. Now, we know how to prevent this, and I'll show you this in a second. No? We just have to switch our logical pattern from a human, semantic, logical thinking to something that we know, Python, C++. A simple computer script would execute this algorithm flawless with a huge number of these. There would be no problem at all. But our giant, sophisticated neural network, our transformer that we have with optimization to the max, could not find the solution. On the one hand, you might say, hey, great, we have tools, no? Tools where we have our C++ environment or a Python environment or whatever you like. So yeah, MCP protocol, tool connection, we just give this to the tools and we get it back. Yes, but it also means that our transformer are not really able to reason or more than a particular threshold. If we reach a threshold, the reasoning disintegrates. And yes, of course, I have shown you here the latest Gemini 2.5 Pro preview. This is now 2 days old. You can have not only the temperature slider, but in the syncing, you have active syncing mode. You could set your syncing budget here from very low here up to 32K. So this is exactly what they are also implementing here in the very latest model. And if you have seen here the original Keivan 3 implementation, and if you work on the Keivan 3 platform, you also see they have a syncing budget here where you can also go here with a slider up to 32K in the syncing token. And it is really worth it because I've showed you at the beginning of the video, if you set for a Claude Sonnet 4, the syncing budget to 0, you get a result that is not at all correct. But if you set it to max, you get a correct result here, even for a simple test. So this here is the paper. Of course, it is not an archive. No, this is here Apple. Come on. So you have to go here to machine learning site here at apple.com at papers. You have here a particular link here. Yes, beautiful. So great paper. Have a look at this. I like it. Thank you to all the authors to showing us here something really interesting. Yeah? And I thought it's kind of a critical reality check, no? Because I had assumption about AI reasoning, and especially about the power of reinforcement learning that would push us beyond those thresholds. And now this reality check was really something, I tell you. No? So it tells us that those models, or this large reasoning models in particular, are doing is less like human reasoning, a complex reasoning structure, and AI is more like an extremely advanced form of pattern matching. And now be prepared for the next words, that only simulates reasoning, but does not really come close at all to real reasoning. This is a great pattern matching machine, and this is it. So therefore, great. So one insight was, hey, there's large reasoning models. You know, it's not just about making them bigger and bigger and bigger and how many, I don't know, billion, trillion, quadrillion free parameters. No, we have a much deeper problem. Yeah? We must overcome at first these fundamental problems that are, or limitations that are clearly visible now with this particular test in Apple. Yeah? So the thinking we see is not robust. It is not a general skill of those reasoning models. No? It operates here best on a particular sweet spot, a sweet interval, and it collapses here in a very predictable way. And this is the amazing thing. No? It's not just a chaotic system. It collapses here absolutely predictable when the complexity exceeds here a certain threshold. This is it. And when truly challenged, our reasoning models here, the effort is now really counterintuitively decreases here now its effort, its reasoning token here, which is also a fundamental scaling limitation. More is not better. So, struggle not only with finding solutions, but even with the following explicit instruction, highlighting here weakness in the logical and procedural execution, because I always thought if I provide a few short examples to my in-context learning prompt, it would help the problem, help to solve the problem. But as we see here, if we follow Apple, no, it did not. Absolutely fascinating. Okay, this is the end of the video, but if there are some experts that say, hey, are there some deeper problems for some experts? Well, yes, of course. So if you say, okay, this is it for me, I say, thanks for watching. But if you want to continue, hey, let's go. Now, they found some interesting topic now, and they looked at Claude 3.7, and they said for one particular puzzle environment, the Tower of Hanoi, it turns out that this is really famous. This is always in the textbook. You find all this example on the internet everywhere. So it's really known. And they said, you know, the problem, the Claude 3.7 model had no problems generating nearly 100 moves, consecutive moves here, which is great, no? Before making a single mistake. But contrary, on a less known river crossing puzzle, the same model that achieved 100 moves could not even manage 5 correct moves on this lesser known puzzle that is not in the textbook, that is not all over the internet. And also the puzzle only required 11 moves in total. So you cannot say that the projection or the prediction here for future moves were too complex to solve. No. Not even 5 moves. And the system collapsed. So this tells us something, yeah? And the authors go here and they say the model has the Claude 317 model has likely seen here an algorithmic motive. So many times that it has developed a kind of a procedural muscle memory for it. It is familiar with all the solution. It has no problem. It has learned so many patterns for this particular puzzle, the Tower of Hanoi, that it can go 100 steps. But a lesser known puzzle cannot even move 5 steps with reasoning. So there is no reasoning. There's only a memorized pattern. Yeah, and they say here, this suggests here to us that what we perceive as reasoning is often the retrieval and the adaptation of memorized solution template, and not a deduction from first principles, from first reasoning principles. So the model is not thinking logical through the puzzle rules, because then it would go more than 5 steps. It is just executing a trained pattern, a behavior it is familiar with. It has seen thousands of times in its pre-training data. And when it encounters a problem for which it has no clear pattern, its supposed reasoning ability evaporates almost instantly. What a beautiful study by Apple. It really throws me back in my belief into the reasoning ability of an LLM. And they say, hey, this thinking is a high variance. It's an unstable strategy. Because you could be lucky and you could find here the absolute correct solution on the first run. But the variance of the failure point is also much, much higher. So this means that the thinking process is a high risk, high reward strategy game that is happening inside our reasoning models. So now we know, even with the best reinforcement learning, it is not stable, it is not a reliable algorithm, and it can fail catastrophically, even with the best reinforcement learning. And I think it's nice, on such simple, trivial puzzles, Apple could deduct some deep behavior of our reasoning model. And yes, I don't know if I agree, but I think I agree. So those standard benchmarks that I showed you, this MAT 500, they are known now for, 4 or 5 years. Everybody knows them. Everybody knows this will be a benchmark that their future model will be tested against. So this benchmark that we know so detailed, that theoretical somebody could train even their new model that this has, a good performance here accidentally. They're absolutely misleading. I don't know if I would say dangerously misleading, but they're absolutely misleading because they only show us one side of the problem, or just one polarization plane of the light. And they are leaving out so many interesting things that even I made wrong conclusion about the reasoning abilities of LLMs. And this is the reason, and a lot of you ask me, why do you design your own test? And you see here in this video, I designed my own causal reasoning test, my own logic test, my own puzzles. And you say, why? There are so many benchmarks available. Why you have to go and you do your own? Because for my particular domain, for my particular task that I want AI to be powerful, I have to design my own tests and I don't publish them on the internet. Otherwise, I would run over time in the same problems that we have with the standard benchmarks, So you see, if you are interested in the performance here and you work in a particular domain, physics, mathematics, finance, healthcare, medical, whatever, pharmaceutical, design your own test. You know exactly what you want from the system. Design your test and you will be amazed by the outcome. And yeah, of course, there was from my last video, from this particular video, I did here the test without here activating here with the new Gemini 2.5 Pro preview, you know, from June 5th here. I did not activate here the code execution. So if I do now the same test like here shown and explained in this video, yes, of course, the new Gemini 2.5 Pro preview writes here Python code or C++. I ask for the Python code. So it can do the code execution. It executes this, it executes here the solver, beautiful. And we find here the code execution result is exactly 6 presses here. This is the perfect solution. You see here 1, 2, 3, 4, 5, 6 button presses here for this particular test that is shown in detail here. And it even tells you at the end, after the code execution, and you see here with the thinking mode, I put just to the max. It says, hey, this demonstrates the power of computational modeling. And this agrees kind of with Apple, no? It is easy to translate here a logical problem into a solver problem. If you go C++, Python, whatever you like. But you write a code solver, and we have so many years of experience that it is easy to write code, and the code has a definite solution. And whatever we as humans or AI, artificial intelligence, thinks now as logical reasoning steps, they can go catastrophically wrong. But with the new MCP protocol, with tool use, with function calling, with everything we have, hey, just connect to a computer modeling, run the modeling, get the performance, and then you continue here with your LLM or large reasoning model reasoning. So just to show you here from the last time, did you know exactly what we're up to? I hope you enjoyed it. I say thank you to Apple. It is always great to see the latest research paper here from Apple. And The Illusion of AI, I think a beautiful paper showing us here clearly the limitation of artificial intelligence. And I wanted to show you, even with the simplest test, you can write some beautiful papers. You can get a deep insight into the current problems of actual current reasoning models here. And it is unsolved. We have no idea where there's this sudden threshold, why there's such a sharp edge in the performance and a decline, and we don't know really how to cope with those problems. If you like to see more kind of videos like this one, why not subscribe? And I see you in my next one.